Well, hey there, everyone. Today here in calculus, we're going to start looking at the error associated by using a polynomial approximation. The idea here is that when you use a polynomial to approximate a function, it's going to come at a cost. The polynomial may or may not give you an estimation that has a degree of accuracy that you're looking for. Now, there are ways to increase the amount of accuracy that a polynomial gives you, but you still need to know, what exactly those errors are going to be, so you know if you need more terms or less terms in your polynomial. So let's get started. So how wrong can our scientists expect to be? This is an important question, since too much error and our astronauts could miss the trajectory completely, assuming that the trajectory is being calculated using a polynomial. And when approximating functions with polynomials, we know that we produce an error of approximation, an error associated with that approximation. So if we're going to use a polynomial approximation, we need to go into it being aware about what kind of errors we're getting and ensuring that our errors are within a tolerable margin. To start off here, we're going to, with our calculator, graph on the same window sine x and the first two terms of the polynomial for sine x. You will remember that the sine x polynomial, the first two terms, are x minus x cubed over 3 factorial. So grabbing our calculator, we're going to put y1 sine x and y2 the first two terms of that polynomial. Then we're going to adjust our window. I've already gone and done that. I'll just go ahead and do this one over here one more time. We want to put negative pi over 2, so negative pi over 2. And that turns it into a decimal approximation, which is just fine. A good thing to do would be to adjust the scales. This tells you the distance between tick marks on the axis. Here I've set it at pi over 4. Y min, Y max, that was supposed to be negative 0.5 and positive 0.5. And I set these tick marks to be at 0.1. So if you adjust the window manually, you will make sure that you push the graph button. And here is sine x in that window. And then here's first two terms of the Taylor polynomial. Did you notice anything? Did you notice that they're exactly the same or close to exactly the same? If I push trace up over in the corner, this tells me I'm at sine x. And if I move over to the right, I see that the y coordinate, the sine of 0.237 is 0.2357. If I push the down arrow, that's going to jump over to the y2 curve. And notice how if the numbers change. The y coordinate is 2357528, 75894. So this looks to be accurate in the, let's see, is that the 5th place? No, 6th place. All the way to here. And that is a 1, 2, 3, 4, 5, 6th decimal place. So if we're looking at values of x that are really close to 0, it looks like, we get a really accurate approximation. All the way to 6 decimal places, actually. So just to summarize that, the approximation is really good. The two graphs are indistinguishable in this window. If we use the trace feature, we can see that the approximation is exact to the 6th decimal place when I look at x equals 0.238. Moving on down, to get a better idea about how well the Maclaurin polynomial converges to sine x, we're going to graph y3 equals y1 minus y3. y2. Be sure that you turn off y1 and y2 and copy the graph below. Over on our calculator, we're going to go ahead and push the y equals button. And we wanted the absolute value, and that's in math number, absolute value of y1 minus y2. And then we also want to turn off graphs 1 and 2. So if you don't know how to turn off your graph, you can just hover on the equal sign, push enter while you're on there, and you'll notice that the equal signs are no longer highlighted. So this says to me that the only thing we're going to graph is y3. I'm going to push the graph function to take a look, and there's that graph. So what does this graph tell us, other than the fact that it looks like a smiley face? Well, this graph is the difference between the actual function, sine of x, and the polynomial function. And if the two functions are exactly equal to each other, then we should get a 0. So any place that we see a 0 in this graph, that's the place where the function and the approximation are exactly the same. If this function gets away from y equals 0, like over here on the left side and over here on the right side, then those are places where the graph and the approximation are not equal to each other, not even very closely equal to each other. Now this tick mark right here is at 0.1, so we can see that the error is less than 0.1, but it's still there. The expression actual minus prediction gives a numerical value for what we call the error of approximation, or sometimes called the truncation error. It's called that because we have truncated the polynomial, the infinite polynomial, to only 2 terms. The absolute value that we used in the formula, that just kind of gives us a sense of the magnitude of the error. So we don't have to worry about positive and negative error. We just think about error as some positive quantity. So, in relation to x equals 0, what is the trend of the error of approximation? Where is the error the greatest? The error, as we can see in the graph, increases at values of x that are farther away or further away from x equals 0, which happens to be the center of the polynomial, which it keeps saying because that is the actual pattern. The further you look from the center of the polynomial, the greater the error is going to be. Now, I talked about this earlier, like how we have ways of dealing with error. So the first way, or one way, is in order to decrease the magnitude of the error, one thing we could do is add more terms to the polynomial. So let's go ahead and go to the polynomial, and we're going to include 3 terms instead of 2 terms. Okay, let's go ahead and go to y equals, and I'm going to keep the y3 over there, and well, I guess I can't do that. So we're going to give ourselves one more term in the polynomial for sine x. That's that x to the 5th over 5 factorial. I want to keep the same window, so I'm just going to push graph now. That'll preserve the window. Since we're graphing on the same window, we can see here that the error has decreased dramatically. Previously, with only 2 terms, we saw that the error was approaching 0.1. But now with 3 terms, the error is, virtually, or this error, the graph of the error, is virtually on the x-axis the whole time. So the error is really close to 0 for most of the interval. How many terms does our polynomial need to reduce the error so that for x equals pi over 2, the error is going to be less than 0.0001? Okay, so let's go ahead and go to our calculator. Let's get to the home screen, and the error is in y3. So we're going to compute y3 at x equals pi over, what did it say, pi over 2 or pi over 4? It was pi over 2. So here the error is 0.004. So that is only 2 decimal places accurate to the 100th place. We'll know we're finished when we get 4 zeros. So now we only have 2 zeros. So in order to increase the accuracy, I'm going to go to the y equals menu, go on down to y2, and I'm going to add another term. So minus to the 7th power over 7 factorial. Probably helps if I put a 7 there, right? And there we go, 7 factorial. Go to the home screen. We'll do that same calculation, the error, and we'll see how many zeros do we get now. Okay, so that gives us 3 zeros. Not quite there yet. We're going to need another term. So we'll go back to the function, add the next term of the sine series, and we'll do that calculation again. Second, enter, enter. Okay, so this gives me 5 zeros, and that kind of does it. We only needed 4 zeros, so we have definitely met that tolerance. So in order to get this done, we needed 1, 2, 3, 4, 5 terms. Next, we're going to write down that polynomial. Great. So that is, what did we say, 5 terms, and the highest power is 9. And if our highest power is 9, what order is that polynomial? Well, that was a 9th ordered polynomial. So this brings us to our important ideas. We have the concept of error, which is actual minus estimation, which is going to be equal to the function evaluated at xi minus a polynomial evaluated at xi. Xi is a place that we call the point of estimation. That's the value of the function we're trying to estimate. Now, if you use a polynomial approximation, the error is going to be literally 0 at the center of the polynomial. And that's because when you construct your polynomial, you're constructing your polynomial starting with f of xi. So of course it better be exact right there at f of xi. As we move our point of estimation away from the center of the polynomial, the error is going to increase. We kind of saw that with that smiley face pink function. The further away we look from the center of the polynomial, the greater the error became. And finally, more terms, if you add more terms to your polynomial, you're going to decrease the error. But with the caveat that the value that you're estimating is in the interval of convergence, which should make sense because if you're trying to use a polynomial for a value outside the interval of convergence, then those results are never guaranteed. Let's check our understanding with number 1 and 2 here. Number 1 says to find the first 2 terms of the Taylor polynomial centered at x equals c to approximate f of x. So if we need 2 terms, that means we're going to need at least 1 derivative. So we're starting off with the function itself, f of x. Our first derivative is 2 over 1 minus 2x squared. We want to center at 0 because c is equal to 0. F prime of 0 is equal to 2. Next, we write the general Taylor polynomial centered at x equals c. We'll go ahead and substitute our value of c, and then we're going to substitute the value of our derivatives. Okay, f of x is approximately equal to 1 plus 2 x minus 2. Now it says to use a polynomial to approximate f of a. Here, a is equal to 0.22. Had to fix one small typo there, but this gives me f of 0.22 is 1 plus 2 multiplied by the quantity of 0.22 minus 0. And that's 1.44. Next, we're supposed to find the error of approximation. So to get the error of approximation, we're going to need to know the exact value of the function. So I'm getting that f of 22 is exactly equal to 1.78571. By definition, error is the absolute value of error minus actual minus predicted. And that gives me that the error is equal to 0.34571. Scrolling over to the second problem, we've got f of x equals cosine x, and c equals pi over 6, and a equals 0.5. Now this presents an additional problem because normally I would just use the Taylor polynomial, or the Maclaurin polynomial, the Maclaurin polynomial, but here they're asking for a center that's not 0, so I have to start all over again. So let's get the first two terms here. I think I'm going to need 3 derivatives here, just because I know the just one derivative is fine, one derivative. So f of x is cosine x, and f prime of x is negative sine x. So f of pi over 6 is cosine of pi over 6, which is rad 3 over 2. F prime of pi over 6 is negative sine of pi over 6, which is negative 1/2. We'll write the general polynomial for a 2-term or first-ordered Taylor polynomial. Then we're going to go substitute our pi over 6, which is our value of c. And then we substitute our values of the derivative, which we got earlier. That's part A. Part B, we want to estimate f of 0.5. So we substitute we substitute 0.5, and the estimation is root 3 over 2 minus 1/2 of 0.5 minus pi over 6. Grab your calculator. I get that the estimate of f of 0.5 is 0.87782. Lastly, we're going to compute error, and error is actual minus predicted. Substitute our approximation for the cosine of 0.5, and then our estimate of the cosine of 0.5. And we can see that our error is really, really small. It's 0.00024. So that's our day for today. Not too bad. We're just really starting with the concept of error approximation. Things will definitely get a little bit more intense when we pick this up on the next lesson. But hopefully if you can get these basics down, then the next lesson will be a lot easier. So we'll see you next time. Have a great one.